This video is brought to you by Astronics Test Systems and the Freedom brand of Communications Systems Analyzers. The topic of this video is Process Automation Toolkit, PAT. It will guide you step by step how to write, save and execute PAT test scripts. How is this presentation structured? We will study the PAT concepts, R8000 series zone prerequisites when writing a test script, a review of the remote command library, writing, documenting, editing and debugging a script, saving and recalling a script, and the use of operators for decision making within that script. So let's take a look at the history of PAT. The development was primarily to provide a method to simplify the automation of the R8600 in ATE systems. While some customers might prefer to use a PC-based programming environment such as C++, this requires a highly skilled programmer that also understands the R8000 M&C command structure. PAT removes the need for these skills and enables a radio test technician to automate tests that in the manual mode require several interactions, menus, and recording of the test results. If you know how to test the device under test manually, PAT can automate it for you. So if you can conduct the test manually, it can be automated. The easiest way to get started is to document the steps needed to conduct the test manually, remembering to document the zone changes that you make during the setup parameters. Basic settings needed to test for the test configuration like test frequency, attenuation, RF bandwidth, port to be used, and then document each zone and menu key you use to perform the test, and then open PAT and insert the documented steps into the script. Before we get started, we need to understand some prerequisites that are needed when writing a script in PAT. To set up a test in manual mode, you must first select one of the 4 zones to access the functions within that zone using the menu keys. These are the RF zone, the audio zone, which in digital modes becomes P25, NXDN or the DMR zone, display zone, and the meter zone. Well, PAT has exactly the same requirements or prerequisites when writing a script. You must always add a zone command before adding commands that would be found in that zone. If you see a not available at this time message, just go back and insert a zone command above the failed line. What are the benefits of automation? Firstly, significantly reduced test times compared with those we would make in manual mode, fully repeatable results regardless of the operator, and the documentation of test results. 2 connection methods are available to PAT, either a direct RJ45 Ethernet connection or a Wi-Fi DCHP network connection. When using the Wi-Fi connection, PAT automatically searches for R8000 presence on the DCHP network. If an instrument is found, it automatically connects. When using the RJ45 Ethernet connection, on the instrument select Settings, Network Setup, and note the IP address. In PAT, select Search and enter the R8000 IP address in the field provided. Now let's take a look at the PAT library structure. All of the analog and digital R8000 series remote operating commands are in the PAT library. These emulate the keystrokes that you would make in manual mode to make a test. The commands are structured in groups that may be expanded and contracted using the positive and the negative tab. Here are some examples of the PAT structure that show several of the menus expanded and showing the familiar legends that are to be found on the R8000 in a manual mode. Looking at these reinforces the simplicity of the PAT interface and the ease of writing test scripts for a non-programming engineer and technicians. Now we have the basics down pat, no pun intended, we're almost ready to start to write our own test script. So firstly, select the required command, in this case test mode, click Add, then select Set, followed by Set To, and if required, select the action from the drop-down menu. Note, most commands have a get function as well as a set. This allows for the program to query the R8000's current settings. Adding descriptive text to a command. Text may be entered to better describe the command's purpose and action, and the benefits are to better describe the action the command will make. In this case, we edited test mode to read set current test mode to standard. This makes the script easier to read and understand its functionality. The underlying command is not affected in any way. To make this edit, click on the command and enter your new description. This also makes it more understandable for later review, debugging and editing. Here is another example of description text. We changed the command that was plain Jane system mode to read set system mode equals monitor, describing better the action of the command. Manual command entry. Please note you must be connected to the instrument to use this feature by either Ethernet or DCHP. The manual command field is populated with the currently selected line. Pressing send command will check the validity of the command and the R8000 will return success or an error message. This feature also enables debugging of a script by executing the script line by line. Adding comment lines to your test script. These comments are non-executable and allow the writer to document why and what a command or a selection of commands are performing. This makes it easier to read later as it documents the writer's reasoning. Comments are unlimited and do not slow down a script's execution time. Some test scripts may require operator interaction with the test script. This script example demonstrates the use of the pause operator. Inserting a pause halts the test script execution and requests an operator action that be needed to perform the test. To add this, after adding the pause, click on the field to enter and edit the displayed text and enter your message. Here we see the pause in action. In this case, set radio channel and press the PTT to make transmitter tests and press continue to move on through the rest of the script. Now we are ready to test our script. To do this, press execute. The script will run sequentially and a scrolling progress bar is displayed during execution in the bottom right hand corner. If the script encounters any errors for any reason, the execution will terminate and an error message will be displayed. When the script is completed, a test report will be generated and displayed. Standard Windows functionality is used for saving files and test results. Folders may be added as in the normal Windows file structure. Save results are in a .csv format. The open key retrieves the selected test report and exit returns you to the main application. Formatting a test report is achieved by the inclusion or exclusion of each line of the script from the actual test report. This allows us to remove setup commands and commands that are not relevant to the measurement results. A standard Windows file structure is used for the saving and recalling of test scripts. Folders may be added as in normal Windows file structure. Delete removes the script from the folder. Load loads a selected script for execution or editing, and save saves a script to the Windows file. Concatenated scripts. This enables us to run two or more selected scripts for concatenation and runs two or more scripts consecutively. Here we see two concatenated scripts. The first one was an analog TX test on a radio that had both analog and digital capabilities. So it ran through the transmitter and receiver test on the analog side. Then it followed on into the DMR mode to test the transmitter and receiver in the digital DMR mode. PAT has the capability to control external devices connected to a USB port, such as relays or switches. External devices communications comms port setup is achieved on this screen where we can select the COM port, the bitrate, the parity, data bits, stop bits and such, and the format is currently in hex, and the program will convert the required command that goes to the relay or the switching into the hex format. Advanced features and functions. PAT has several capabilities and features and functions that are somewhat beyond the scope of this presentation and require a more in-depth explanation. Essentially, they are: we can optimize the speed for each step, the default timings for each line are conservative and the test scripts can be speeded up. Variable, nameable and processable counters. You can set the value, increment value, decrement value. Variables are used for things like loop counters and text such as pass-fail indicators. Copy and paste. You can click on any line in the script, copy it and paste it anywhere else within the script. Drag and drop lines. You can rearrange the script order. You can grab a test that's at the bottom of the script and take it to the top, or insert it anywhere inside so it rearranges the order of the script. Another advanced feature of PAT are decision-making operators that allow us to make logical decisions within the script by go to line else, go to line end if line x equals greater than, less than, equal a value, then do something like pass, or else you do something else like fail, and you end the loop by end if. Over on the right hand side of the picture here we see a loop that tests receiver sensitivity for 12 dB SINAD, and each loop around reduces the level by 1 dB, and when we get to a decision point where SINAD equals 12 dB, we jump out of the loop and read the RF output level, which equals the receiver sensitivity. Currently running factory defaults. On the right side of the display we have PAT with a test script already loaded. And yes, you can run RFP and PAT simultaneously. As we execute the script, we'll be able to observe the R8100 under PAT remote control. This is especially useful for test script debugging. As we can see in the script, I have made several comment additions to make it more understandable, such as script title, audio configuration, RF configuration, start RX test, and I've edited the commands to make them more understandable. Let's first examine and execute the script line by line. To edit and debug a script, we will use the manual command entry to send commands directly to the R8100 and look for a positive response from the instrument. So you simply select the line in the script that you wish to send the command directly to the R8100. In this case, current test mode equals standard on line 1. It's loaded the manual command entry with that command. Send the command, and the R8100 will return a positive message saying yes, I've gone to the standard mode. Because we're testing a transmitter, I also need to be in the monitor mode, so select line 2, send the command, and the R8100 has gone to the monitor mode. Next I must go to the audio zone to set up an audio oscillator, 1 kHz audio oscillator, to provide the stimulus to the microphone of the radio under test. So select audio zone. R8100 has gone to the audio zone. Now remember the prerequisites. You have to be in a zone to use the commands from within that zone. So I had to go to the audio zone to be able to set up this audio oscillator. So I'm going to set the fixed 1 kHz level to 200 millivolts. Send command. And then need to turn the audio oscillator on. Set to continuous. R8100 confirms that the audio oscillator is on in a continuous mode. That completes the audio setup. Now I need to go to the RF zone, so line 8 command sends me to the RF zone. Again, prerequisites, we must be in the RF zone to use RF zone commands. Next I'm going to set the monitor frequency to 851.0125. Send command. Modulation type is FM. Bandwidth is 25 kHz. RF attenuation is 30 dB, RF monitor port, that's the port of which I've got the radio under test connected to, is the RFIO. Send command, and that completes the configuration. Now let's review the measurements we're going to make when we press the PTT on the radio. So start TX test. First thing that will happen is I have a settling time of 3 seconds for the RF amplifier in the power amplifier in the radio to settle. I'm then going to read its input level in dBm, frequency error in hertz, deviation positive and negative in kilohertz. I'm going to release the PTT, and that will be the end of the test. So let's go back to the top of the script and get ready to execute. And we're going to execute the script And I'm going to have to press the PTT and 3 hands to also select the continue. Press the PTT on the radio and we can hear the 1 kHz tone coming through the speaker of the radio. Press continue, 3 seconds wait time. It made some measurements, release PTT, press continue, and here we had the measurements. So 30 dBm, 1 watt, frequency error 21 Hz, plus and negative deviations 2 kHz, basically plus or minus 2 kHz. And that would be the end of the test, and it saves them in these test results. Now, while we're taking a look at this, let's cancel that exit from that test and talk about the included excluded, because we don't really need any of these to be in the test result. So I can select each line and exclude, 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 exclude. I think you get the idea. I will leave it there, and then I'll execute the test again, and you'll see that all of those commands have been removed from the test report, leaving just the results. So execute again. Press the PTT, 3-hand job again. Press the PTT, continue, make the measurements, 3-second wait time, settling. Release the PTT, continue. And we can now see that all of those tests that I excluded, or all of those commands that I excluded, no longer show in the test report, basically leaving the results, which are the only things that are of real interest. And of course I can save this off to a windows.csv file. And that concludes the end of a simple PAT test script to test an analog transmitter. In this video clip, we're going to test a DMR radio's transmitter and receiver. We'll be able to watch the R8100 obey the commands to go from standard that it's in currently into the DMR mode, set up the configuration and make the measurements. So press execute. Get ready to press the PTT and you can see it going through the setup. You'll see in a second on the R8100 it will go into DMR mode. And then we'll carry on down, asking me to press the PTT. So press the PTT and we'll see the TDMA signal shooting up and down on the spectrum analyzer and the measurements being made. If I hit continue, then these automatic measurements will be made. Release the PTT, it will go into generate mode and generate a 1031 Hz tone, and we'll be able to hear it come out on the loudspeaker. Continue. And here we have the test results. Now you'll see that I've already optimized this test report to take out all of the setup parameters and just give us the test report of the measurements that we consider most relevant, which are magnitude error, FSK error, symbol deviation, and the RF receiver sensitivity, a measure of the RF receiver sensitivity. And that concludes DMR transmitter receiver test. This video clip is a straightforward configuration and test setup for testing an NXDN transmitter receiver. So pressing execute, we will run through the setup in both the RF parameters and the NXDN parameters. It will then ask me to press the PTT. So press the PTT and continue. Measurements take place. And it will ask me to release the PTT, continue. And at minus 119 is roughly the receiver sensitivity, or an estimation of the receiver sensitivity, and we can hear the tone coming through the speaker of the radio. Continue. And it will bring up the test results so we can take a quick look at the test results. Bit rate was 4800, The frequency error was 45 Hz. Typically we need them to be less than 100 Hz on a digital radio. Modulation fidelity is less than 1%. Symbol deviation 1062. We started the BER test, gave it 2 seconds to settle in the BER numbers, and got a result of 1.2%. Stopped the BER, moved on to the generate side to test the receiver, set a level of -119, generated a 1031 Hz tone and waited for it to come out of the speaker. As we saw, everything was successful, so that is the end of the NXDN test. This video clip shows us a test of Tetra TMO trunking, a very complex script because it has to set up so many parameters from within the channel setup and various parameters that have to be set up for Tetra TMO, such as base station color code, mobile country code, mobile network code, area codes. We have to be into the right time slot with the right select channel offset. So depending on how the radio is programmed, depends on how you set these parameters up. This makes it into a very complex script. But essentially it will do exactly the same as all the other scripts. If I select execute, and it will start to run through the script and set up the various parameters that I was talking about. And it will get to a point after it's set up all of those parameters, the radio will register with what is effectively a base station emulator. And at this point it will ask me to check to make sure the radio is registered, and it is. It has a mobile SSI of 8, so I just ensure that the radio is ready to receive the call. Continue, and we can hear the phone ringing, so I answer the call, and the measurements can now take place. Release the call after the TX measurements are made. We're now going to test the power loop control. So it will step through the 5 levels of power loop control, plus 15, plus 20 next, plus 25 after that, then 30 dBm, and lastly the highest power level of plus 32 dBm. And that's the end of the test. Now I've deliberately not optimized the test results here so that we can see all of the parameters that were set up. So if we come down, we can see we went into channel plan, then we set up the channel frequency of channel 3600, no channel offset, 10 MHz duplex. The manual entry was 390 MHz dead, base station color code, mobile country code, mobile network code, and so on and so on. So we went all the way through, and then when we pressed the PTT and answered the call, then we started to make measurements. So the measurements of RF power in dBm, ideally it would be 15 dBm, so that's very, very good. Error vector magnitude peak must not exceed 30%, and we can see it's well below that at 20%. Error vector magnitude RMS must not exceed 10%, so it's half of that at just 5.8%. Frame alignment must be better than 0.250 symbols, 0.133, that's good. Measure the frequency error. We expect to see the frequency error on a Tetra radio to be better than 100 Hz, and we can see this one is 4 Hz. Residual carrier power, less than 5%, if I remember the ETSI spec correctly, so 1.2% is very, very good. And the unwanted power must be better than minus 37 dBm, and here we can see it's minus 39. Then we release the call. Now wait 3 seconds for it to run through these tests, which is plenty of time for those tests to take place, and I drop into the PLC test, programmable power loop control, sorry, and we can see it runs through and steps through. Effectively what we do is drop the RF power by a certain amount and expect the power loop control to power up in 5 dB steps. So it started at 15, we dropped the signal RSSI level going to the radio, and it developed 20 dBm, 25 dBm, 30 dBm, and the max of 32.5 dBm. In the next 5 slides, we'll take a look at how Pat can assist you in testing your radio for max and min limits, i.e. maximum power, maximum deviation, minimum deviation, and cyanide, and so on, receiver and transmitter tests. And essentially they're based around these operators. So the primary operators for test limits are greater or less than, go to line, else, and a variable that can be user defined, so I can make text say passed or failed, and the end if. In this slide we see the practical application of using the pass and fail parameters, the limits test, to test a radio's frequency, in this case read frequency error, and if line 14, the one above where we read it, is greater than 110 Hz, then we go to line 24, failed. Else, we test again to see if the frequency is less than 68 Hz, and again if it's less than 68 Hz, we go to line 24, failed. Else, the frequency passed, and we jump out with an end if to take the next reading in the next slide. Here we can see those pass and failed test limits being used to test the frequency, as we just saw in the previous slide. And if it passed, we jump around and go to read the power, check the power levels, upper and lower. If they pass, or even if they fail, we read the deviation, do the same test again, look for max and minimum deviation, deviation passed, and then we go to the receiver side. We set the generator up to generate a 1 kHz tone for us to be able to measure cyanide at a level of minus 121 dBm. So we read the cyanide, and if it is less than 12 we failed, and if it's greater than 12 we passed, and that is the end of the test. Here we see the test results from that previous script. So we can see that we tested the frequency error, and it was less than 100 Hz, and so the frequency passed. Obviously we also checked to make sure it wasn't lower than minus 68. We then went on to read the RF level in watts, and it was 1.2, so it was actually not greater than 1.4 and not less than 0.9. Then we go on to read the deviation and check to make sure it doesn't exceed 2.4 kHz. Then we start the receiver test, read the cyanide. Cyanide, as we can see, was greater than 12 dBm, so everything passed. Okay, now let's run the script that we looked at in the previous 4 slides. So we're going to test or demonstrate the PAT script in anger. So first of all, we're going to set up the unit, and then we're going to press the execute key. And the monitor gets set up in parameters that suit the radio under test. Then we come to a pause statement that says select radio channel and press PTT, press continue. The measurements are now taking place and scrolling through at the bottom right hand side of the screen. Release the PTT because we finished with the transmitter test. Now we're going to continue with a receiver test, the receiver sensitivity or 12 dB cyanide. Setting up the unit in the generate mode, level at minus 121 dBm. We're looking for better than 12 dB of cyanide. And of course now the test results have come up, and we can see we were testing on a frequency of 851.0125. Our frequency error was 48 Hz. Our RF output level, RF power level is 1.47 watts. Our deviation is 2.08 kHz. Deviation passed, power passed, frequency passed. Onto the receiver test, set the level at minus 121 dBm and look for 12 dB cyanide, and indeed it was 13 dBms. We have reached the end of this presentation. During the presentation we have learned how simple and intuitive PAT is to write your own test scripts. No programming knowledge or experience is required. If you know how to make the test on your DUT radio manually, PAT can automate it. PAT includes all the commands that emulate manual manuals of the R8000 series. PAT generates full test reports that are saved in .csv format for archiving. For additional information and step-by-step instructions, please find the following app titled Process Automation Toolkit User Guide in the document library on the Freedom website.
Please check our website for product information such as data sheets, brochures, operators manuals, user guides, application notes, and other videos. Contact information for our sales and application engineers is on the support page. To schedule a product demonstration or to obtain pricing information, contact your local U.S. manufacturer's representative or international distributor. You can also connect with us through social media channels. On behalf of the Freedom team at Astronics Test Systems, we trust you have found this presentation useful and hope you will reach out to us and let us show you how our expertise, our experience, and our products can save you time and money as you endeavor to keep the radio communications flowing on your systems.